Good afternoon, everybody. My name is David Bott. I'm chairing this afternoon's SCItalk, and it's my pleasure to welcome you to what is going to be a fascinating exploration of things. So just to go through a few bits of pieces, this is a talk about lithium-ion batteries, and I'll come on to why Melanie is exactly the right person to talk in a minute. And what we're going to do is talk about why lithium-ion batteries that we know are so important for all forms of transportation going forward are not perfect. They go wrong occasionally, and what Melanie's been doing for a number of years now is trying to work out why they go wrong and how to stop them going wrong. As I said, I'm chairing it, and I obviously look like that after 3 months in lockdown, and I'm helped this afternoon by Heather and Bryony, who will help coordinate the Q&A at the end of this session. So that you know, on your sidebar there is a thing that says questions. You can put questions in at any point during the stage, and they will bundle them up, and so that at the end, when Melanie's finished talking, she will answer them in groups. So that's right. Right, so you're all in listen-only mode, you're muted, you can't speak. And as I said, there'll be a Q&A session at the end. Type your questions in at any point. If you don't type them in towards the back end of the talk, Heather and Bryony will be panicking and trying to work out what they're going to open the session with. So please ask questions, think about them, throw them up when you think about them, and Mel will answer them at the end. So Melanie is at the Warwick Manufacturing Group. She's Associate Professor of Electrochemical Materials. She has been working in this area for many years now. Before WMG, she was in Nexion, which is a startup working on materials for energy storage, and she is associated with some of the biggest programs going on. The Graphene Flagship is a European program, the Faraday Institute is a British program, and it's about how we understand batteries of all sorts, but primarily lithium-ion at the moment, and make them right for the use that we're increasingly using them for in electric cars, electric trains, electric buses, and even now we've got short-hop electric airplanes. So Melanie is an expert on this. She's also appeared in a number of videos by the nice Mr. Robert Llewellyn on Fully Charged and around WMG, and she's an acknowledged expert in the area and great at explaining things. So Melanie, may I pass across the baton to you, and you can give us your talk.
Good afternoon, everyone. My name is Melanie Loveridge. I'm an associate professor in the Electrochemical Materials Group, and I'm going to talk to you today about why lithium-ion batteries degrade and lose capacity, or as I like to see it, the Iliad and the Odyssey for lithium ions. So let's go back to where it all began, which was a truly global innovation. And so this year marks the 29th anniversary of the launch of an energy storage game changer, which is the lithium-ion rechargeable battery. So it was first invented in 1991 to power the Sony camcorder. And so why it was a truly global innovation is that, so John Goodenough in Oxford University invented the layered lithium cobalt oxide cathode material. Stanley Whittingham in Binghamton developed a disulfide cathode material based on titanium and cycled that in a full battery against a lithium metal anode. And Yoshino in Japan first developed a carbonaceous-based anode, initially on petroleum coke. So he was able to use the cathode chemistry and cycle a full cell, which has become known as the batteries that we know now. But I have to say that respect has to be paid to Rashid Yamaki, who developed the first actual graphite intercalation anode, and for whatever reason he was not part of the Nobel Prize list, which for reasons that I can't go into today. Since 1991, lithium-ion batteries have been very effective for the so-called 3C markets, which are computers, consumer electronics, and communications. And that's been fine for the low demands of energy density and power. But since we want to electrify the world, the larger format devices obviously pose performance demands in terms of both power and capacity. And so in the last decade, we've really ramped up in automotive electrification, which has put some serious challenges on lithium-ion technologies. Okay, so the challenges associated with powering large format devices for longer range and delivery. Slow charging times are a big concern because it's with computers, laptops, phones, you can leave these things charging for quite long time periods, but it's a bit different when you come to vehicles because you can't always have the luxury of being able to just charge these overnight. Battery materials supply has made the headlines with, you know, whether it's ethical considerations running out of lithium. And also, if we're going to have a serious uptake in electric vehicles, we're going to end up with a lot of used batteries to recycle. And so these are all big concerns for scaling up of the size of batteries that we need. But hope is on the horizon because there are constant innovations in new battery materials, chemistries and components to make advanced, longer lasting, more powerful batteries. Progress has been underway in rapid charging technologies and charging infrastructures to reach this net zero. So one of the initial cathode materials, which contains a lot of cobalt, there have been a lot of concerns about the ethical issues surrounding these materials, including their toxicity. And so alternatives are being used for this. For example, higher nickel cathodes are making great progress, both in research and commercially. There are alternatives to lithium-ion technologies such as sodium-ion, and of course, compared with using virgin materials for manufacturing, we are seeing a lot more investment in recycling, both in methodology and innovations. And so there's an enormous potential for battery supply chains to capitalize on this, as we can see here. So the recycling of lithium-ion batteries could prove very profitable for the UK. So the blue line or succession you can see are the routes through battery manufacturing, from the mining of the initial materials, the refining of them to make them usable, both in purity, content, and size, morphology, and then all the way through to the electrode manufacturing, the actual battery use, and potential second use considerations going forward. Because of course, at the end of the day, you know, if we're ending up with millions of these battery packs, modules, cells, we need to avoid as much as possible what goes into landfill. And so we have a lot of options around recycling, reuse, reselling, and refabricating, which at the end of the day is going to be great for the world, but especially if we can generate UK-based supply chains and recycling facilities. So it has been said by the founder of circular energy storage consulting, Hans Mellin, that lithium-ion batteries are one of the most circular products you can actually see, because there are a number of entry points throughout the battery manufacturing chain that recycled as opposed to virgin materials can be used. So that's great, that's all fair and good, and set the scene. So now I think it would be useful to go inside batteries and see what happens in terms of their performance, but more importantly, why does it fade? So at the end of the day, it is all about the incredible journeys that lithium ions have to make. So why lithium? Well, first and foremost, lithium ions give up their outer electrons in their atoms very easily to become lithium ions. And you can see this in the schematics at the center bottom of the slide. But also, lithium atoms are very small, and this means that they can fit inside or insert into other materials quite easily without disrupting the material too much. And as electrons are charge carriers, small atoms that can give up electrons very easily make them really good sources of charge or electricity. So for those of you listening who know what batteries are composed of, the following few slides will be quite familiar to you. Quite often we mistakenly use the term battery. A battery is actually a collection of cells, but we tend to refer to individual cells as batteries. So what you can see on the screen on the left is a battery pack from a Nissan Leaf car, and on the right, a battery pack from a Tesla. If you look inside these battery packs, you see subcomponents called modules that obviously completely look different between the Leaf and the Tesla. And this is because in the Leaf, we have individual cells known as pouch cells for obvious reasons. Inside a Tesla, we have a different format of cell that is known as a cylindrical cell for obvious reasons. And then when we look inside these cells, the configuration of how the electrodes are stacked is actually very different. So in the pouch cell, we can see a sort of a lasagna type effect where the anodes and the cathodes are stacked and separated by what is called a separator, which is an organic porous film that stops the electrodes touching and electrically short-circuiting, whereas in the image you can see on the right, the components, the layers, are actually wound into an Archimedean spiral. So they are very different. But when we look inside the layers, so on the left, you can see a cross-section of an anode coating, which is composed of graphite particles with conductive additives and a polymer binder to make sure that all the components are coherent, but also adherent to a current collector, and are porous enough to allow an organic solvent to infiltrate all of the coating to enable lithium ions to diffuse efficiently and uniformly. The electron image on the right shows a cross-section through cathode coating. This is based on transition metal oxide. And as you can see here, the not very uniform distribution of conductive additives, and they're all electrodes are separated by an insulating and porous separator, which is typically a tri-layer laminate based on polyethylene and polypropylene. And then inside the batteries, we have what we call the active materials. So these are particles of certain chemistries that will reversibly store the lithium atoms. So since 1991, graphite has been the anode active material of choice because it becomes active with lithium ions at lower voltages. On the right, this is a nickel manganese cobalt oxide. It's a sort of micron-sized aggregate of lots of sub-micron grains, and this is a typical cathode material of current commercial interest. But because these both anode and cathode active materials need to be very conductive, obviously graphite is, but they still need higher surface area carbon additives to make sure that the bulk of the electrode coating can convey electrons in X, Y, Z directions. And they all need to be held together by a sticky polymer film. In the case of this one that you can see in the center bottom, this is a polymer called PVDF, or polyvinylidene difluoride, which has been, I think it's fair to say, a bit of a workhorse polymer since the initial manufacture of these batteries. And so back to basics. I'm sure most of you listening know how a battery works. This is a simplified cross-section of a single full cell where you can see the anode on the left, cathode on the right. So the fact that they are separated by an insulating separator means that lithium ions can pass to and from the electrodes, but electrons are then forced to pass through an external circuit. So during the charging of a battery, or when your battery is plugged into the mains, lithium ions leave the cathode and travel through the separator to the anode. And at the same time, electrons pass through an external circuit to reach the current collector of the anode. Then when you discharge a battery or use it to power a device, the lithium ions move the other way and the electrons go through an external circuit to actually power the device. So this is a very simplified way of describing battery operation. So before we delve into ancient Greece and I launch my analogy of the Iliad and the Odyssey, I think it's probably quite useful to think about the degradation modes that occur in batteries. And it's by understanding these actually that has led to improvements and incremental changes in battery component manufacturing and quality. So first of all, I'd like to share with you some of the dominant degradation modes in the anode component of lithium-ion batteries. So first of all, when we first charge a battery, we make some significant chemical changes on the surface of the anode. So you can see the schematic on the left. We generate at lower voltages some partial electrolyte decomposition. Now, the electrolyte is based on a combination of a number of organic carbonate solvents, so chosen because they have very good diffusion properties for lithium ions. And so you can see on the left, it's depicted rather simplistically, but the solid electrolyte interface is a very complex structure. It's a passivating film that forms with the decomposition products from the electrolyte breakdown and some of the lithium ions from the electrolyte salt. And you get this very interesting combination of inorganic and organic phases, which irreversibly consume a ballpark about 10% of your lithium, which acts as a charge carrier. So it's a partial reduction in the lithium inventory, which causes an initial hit on the capacity. So this is what you can see here on the left. And in the TEM section diagram, so images on the right, these passivating layers are of the sort of nanometer dimension. They're quite thin and not always continuous. And so it's very important that they passivate the underlying active substrate to stop it further reacting with decomposing electrolyte, but they have to remain ionically conductive so that the lithium can convey charge in and out of the active materials. So that's the first degradation mode of the anode, in that it uses up irreversibly some lithium. So another significant mode of aging in anodes is lithium plating, which can have associated safety concerns. And this is a lot to do with the magnitude of the current that is experienced by the anodes. So you see this plot in the middle here that divides sort of high and low currents with the type of plating you can get at very low potentials, because this is approaching the plating or the reduction potential of lithium itself. And so on the left here, with low current densities, you can get quite a uniform or sort of mossy lithium deposited that is associated more with low current densities as experienced by the graphite or whichever other anode. But when you move to high currents, you start limiting diffusion properties. And so you get this higher aspect ratio or sort of branch-like lithium deposited, which are known as dendrites. Now, in a worst case scenario, when these are able to penetrate the organic or the insulating separator, they can cause a short circuit, which can be quite hazardous in lithium-ion batteries. But generally, any kind of plating is not overly problematic, other than it depletes capacity because it uses up lithium that you can't then get back. But in a broader sense, because we have obviously a number of different current densities depending on the cell type, whether it's an energy or a power cell, so generally you can get very different types of plating morphology, but they are typically categorized as mossy, dendritic, or more whisker-like in between. And it's really interesting how they grow. So this very simplified schematic on the screen shows SCI growth on a lithium anode. So here you can see various electrolyte components that when they enter into lower voltages start to deposit these SCI passivation layers. And the SCI initiation is not always uniform. And so on a non or an inhomogeneous surface, it can act as sites for nucleation where you get localized seeding of nucleates of plated lithium, which you can see at the bottom here, can actually then start to grow through the SCI layer. But the consequences of that is that it then adds more active surface to allow for more SCI to grow. So it's like a constant lithium consumption, if you like. And then as that continues, that's where you get this slow movement and slow diffusion of lithium ions. And so the higher aspect growth and needle-like or fractal progressions develop. And it's this that we need to avoid in case of short circuiting through the organic separator. And of course, there are conditions that can represent what we call a perfect storm for dendrite growth. So this is a cross-section of an anode. You've got your separator, graphite particles, current collector. So in conditions where we've got low temperatures or very high current densities, they tend to be the major culprits for exacerbating dendritic growth. And it's all related to deposition flux and temperature, which can affect diffusion properties and is all interlinked. But the last major categorization of anode issue would be down to the type of material and lithium storage mode. So 3 different modes of anode mechanism that insert lithium. Layered materials such as graphite, which were the initial anode materials, they store lithium by way of an intercalation process, whereby it literally inserts itself between layers. And this can be intrinsic 1, 2, or 3D openings within the particles to facilitate transport. Now, this is great because we don't suffer from any significant structural change or expansion. But the downside of this is that they have limited storage capacity. So then moving to the central group or central modus of lithium insertion, these are elements that alloy with lithium, and these can be metalloids such as silicon or metals such as tin. And the alloying mechanism proceeds by directly bonding between lithium and the host environment. And so the crystalline structures of these materials become amorphous as the lithium inserts itself. Unfortunately, this results in an enormous volume expansion of the material because they can accommodate much more lithium, which is why they can represent a much higher specific capacity. But again, it's always a balance between how much you charge these materials with how much damage you then see within electrodes, because not all electrode structures can accommodate such large volume expansion from the active materials. But the third type of lithium insertion in anodes has looked at conversion materials, which do a direct chemical reaction to form different compounds. Oxides, fluorides are typical materials, but these have made less success in a commercial sense because you do get a very high irreversible capacity loss, because not all of the chemical reactions that these materials take part in are actually reversible. And lithium-ion batteries rely on having this reversible flux of lithium ions between electrodes. Okay, so that's the anode, it's one half of the battery. So the other side, in the cathode or the positive electrode, has another set of degradation mechanisms, which we will now have a look at. Okay, so first of all, cathodes typically based on transition metal oxides of a number of different crystalline structures and chemistries. So firstly, structural breakdown as a function of aging is a common cause of degradation in cathodes. So these materials you can see here, so the image in the top right is a cross-section SEM image through nickel, manganese, cobalt, or a high nickel version, NMC811. And so this is a sort of several micron scale aggregate of lots of little nanograins, and it's very polycrystalline. And so when you start lithiating these structures, you get anisotropic lattice expansions and converse contractions that can result in microcracking, because a lot of strain can develop when these things are expanding in different directions. And this can actually allow electrolyte permeation along these grain boundaries, which we'll see in the next couple of slides will have another degradation mode. But in terms of the operational efficiency, any breakdown in a secondary structure can lead to electrical disconnects between these submicron grains, which will obviously compromise charge transfer and can then lead to loss of active material, which you can see in the bottom right, whereby you get these voids developing where you get disconnections of a lot of the material. So this does literally reduce the capacity of the actual material, which clearly is a dominant aging mechanism. Certain cathode chemistries, such as nickel, cobalt, aluminium, and lithium manganese oxide, upon contact with the electrolyte, can also undergo deleterious surface transformations, which will seriously influence how well and how quickly lithium can diffuse. And this is especially problematic at higher voltage cycling conditions, where the sort of higher capacity cathode materials are needing to operate efficiently. So in such surface transformations, we can see a transformation from the classic layered type structures through sort of spinel bridging phases to a sort of rock salt type crystalline structure, which you can see in this image on the bottom left. So this is an over-lithiated nickel, cobalt, aluminium particle. So we have our nice layered structure in the middle. Then we have this transformation into this type of structure, which is a spinel type crystallography, then finally to the rock salt. And this can add impedance to the particles or make it more problematic for the lithium ions to, effortlessly and effectively transition into and out of the particles, which becomes a lot worse on higher temperatures, when you can also then start to get oxygen release, which from a safety and a structural stability perspective can really compromise the particles. This is another illustration of surface transformations. So the top TEM showing a pristine material. And when we say pristine, we mean non-lithiated. And then you can probably see at the bottom a very different crystalline surface, near surface transformation. We can also get this the other way around. So in the case of a sort of a spinel type LMO material, this can actually transition into a layered structure upon aging and heating. And also we can get different gradients of oxidation states in single particles. So this schematic on the right is showing single nickel-rich oxide particles that were analysed and characterised using phytography. And so in the red image here, you can see gradients of oxygen loss, or in the middle, areas where there is inactive or trapped lithium. And the image on the right is showing sort of bulk oxidation states due to lithium extrusion. And all of this can really compromise carrier transport in the particles, which is clearly the efficient way that lithium-ion batteries operate. But also, in addition to that, secondary reaction pathways can be generated that are linked to oxygen evolution, which we need to avoid to maintain optimal battery performance. So the third, and by no means less significant, aging mode in cathodes, just as we saw earlier, when you first form a battery and you start to passivate the surface of the anode with the solid electrolyte interface layers, something similar happens on the cathode at the higher voltages, where the cathode becomes active. So this is called the cathode electrolyte interface, and we can see a schematic of this, which develops on the surface of the cathode particles because of the higher voltage decomposition of the electrolyte solvents and reaction with lithium compounds. And in the top right, you can see TEM images. So again, these films, they are of the sort of nanometer dimension thickness. And it just means that it's another area or another domain whereby we can irreversibly trap lithium. But also, and interestingly, as the cathode chemistry evolution has journeyed into new chemistries, a lot of studies have looked at the dissolution of certain transition metals from the cathode that can inadvertently migrate towards the anode and actually modify the SCI on the anode, which can have an effect on performance. So a lot of studies have been carried out on manganese, but as we're trying to develop more high nickel materials, which contain, so for example, the NMC 811 material contains 8 times stoichiometrically more nickel than the other transition metals. And so there is the likelihood that more of this will then enter the electrolyte, find its way through the separator onto the anode. And this is a current very interesting research area to know what effect can this have on performance. And so as a result of this, with the high nickel materials, which do suffer moisture sensitivity also, passivating these surfaces before they're actually operated, or adding electrolyte additives to try to pin or mitigate this transition metal dissolution, is a very popular current area of research. So, as we've now seen, operating a battery is a cyclical or repeated treacherous voyage for lithium ions. And during the charging and discharging of batteries, lithium ions have to undergo epic journeys. So I like to think of this as being like an Iliad or an Odyssey for lithium ions. So the Iliad and the Odyssey in Greek legend, authored by Homer, ancient Greek Homer, not Homer Simpson, for clarification. But during these epic journeys, not all lithium ions make it. And so let's have a look at the analogy from the battles of the Iliad and the journeys of the Odyssey as to why they don't. So what exactly was the Iliad and the Odyssey? So the Iliad and the Odyssey were both huge poems, all written in iambic pentameter, which, purposes of today's presentation, I decided to not attempt. So the Iliad is centred on the 10-year Trojan War, where the Greeks defeated Troy, followed by the 10-year epic journey back to Ithaca by our hero Odysseus. So straight away then, the Iliad, or the siege and the Battle of Troy, it's a little bit like the SCI formation. So the Iliad centres on the city of Ilion, coincidentally, which is known as Troy. And so in a lithium-ion battery, this is the surface of graphite particles, with the lithium ions being represented by the copious influx of Achaeans or Greeks arriving from Ithaca, or the cathode. So clearly, Trojan War took 10 years, but actually SCI formation does occur over hours, so it's a little bit different. And so what we can see here on the right, as you saw earlier, this schematic of the SCI could actually be like an aerial shot of the siege of Troy, where you have your gateway to Troy being the SCI film and the graphite actually being the city of Troy itself. And so for lithium ions, safely moving through the electrolyte solvent and the SCI layer is actually critical to them being able to efficiently convey charge. And so in this central image here, you can see this little green circle. This is a lithium ion, and it's surrounded by a solvation sphere from various electrolyte components. And so we can kind of analogize these as being sort of protective organic ships, like you can see on the top left here, to convey the lithium ions safely to the surface or the shores of the graphite particles, which we can see here in a slightly simplified schematic. So we've got all of these solvation spheres dropping off lithium ions at the SCI port, which the SCI has a more sort of compact inorganic and a more porous organic layer. So it's a kind of two-layer port, if you like. But they still need to get through the SCI safely. And this is where we have advantageous ionophores, or sort of ionic Trojan horses, and diffusion vacancies and channels that can get the lithium ions through the channels so that they can get into the intercalation of the anode material. And so arriving and breaking through the gates of Troy, which you can see depicted energetically here. So losing the solvation sphere means they can effectively charge into the graphite through the sort of the gateway to Troy, or the SCI layer, in order to then intercalate into a maximum diffusion space so they can fully get into the graphite particles. That, in a nutshell, was the siege and the Battle of Troy. So then, after the Greeks did that, the massive journey back towards Ithaca for Odysseus formed the second part of this epic poem. So let's see what that looks like for lithium ions. This is a map of the journey from Troy to Ithaca for Odysseus in the Odyssey. And as you can see, this journey is a little bit convoluted and not exactly as the crow flies, as we say. But to be fair, the tortuosity and diffusion pathways for lithium ions on the way from the anode back to the cathode are as problematic and tortuous. So Odysseus's journey to Ithaca took another 10 years. And if only lithium-ion batteries could maintain the charge for that long, they'd be incredible. But so both Odysseus and lithium ions had surprises in wait for them on their epic return journeys. So when Odysseus got back to Ithaca, let's bear in mind he'd been away for 20 years in total and was assumed dead. This shows a sad picture of his wife Penelope, who had been besieged by suitors wanting her hand in marriage whilst Odysseus was away, and he had to battle through these on his return. So cunningly, during his absence, Penelope wove a funeral shroud for Odysseus, and she promised to all the suitors that she would choose a husband when she finished weaving this funeral shroud. So this actually was a protective shroud that in the end saved her. So lithium ions, coming back to the cathode, have to battle their way through the cathode electrolyte interphase, which coincidentally acts as another type of protective shroud in a very different sense. Also, on the journey home, Odysseus was faced with a very treacherous journey, facing a lot of horrible monsters and beasts such as Cyclops, or the bewitching Kirke, which I'm told by a Greek colleague that is the actual pronunciation. The seductive sirens, the horrible Charybdis, the giant Lestrygonians, the land of the dead at Tiresias, and of course the very odd lotus eaters. And whilst lithium ions are not necessarily faced with molecular monsters on their journey back to the cathode, they don't exactly experience a walk in the park either. So this is a reasonably simplified cross-section of a full cell that you'd find within a battery. From the left, where we have the anode, negative electrode. So the current collector for the anode is made of copper, and this can corrode. The electrode coating containing all of the active materials that are adhered to this to convey effective charge transfer can also delaminate as a function of aging. In the active particles themselves, they can exfoliate and sort of start to break down. They can trap isolated lithium, and the constant SCI decomposition, they can plate out lithium. They can have porosity in the electrode that blocks up and so makes it so much more tortuous for the lithium ions to move. And this is before we even get to the cathode, which, as we saw earlier, has its own set of tortuosity and degradation and aging mechanisms, as well as corrosion of its own current collector. And so this also is a treacherous journey for lithium ions. Also, let's put it into context. So Odysseus only actually made one cycle, which took 20 years. Lithium ions have to do hundreds, if not thousands, of cycles in a couple of years. So at a C rate of 1 C, as we say in battery speak, 20 years would equate to 180,000 cycles, which currently no commercial cell can do. And so also, interestingly, comparing the size of Odysseus to the distance he travelled, to the size of a lithium ion and the distance they have to travel, you can see that the ratios are considerably different. And in reality, this distance cited for the lithium ion size to distance ratio is only for the journey through the separator. It doesn't take into account the tortuous diffusion through either the cathode or the anode. So in that respect, who's the real hero? I'll leave that one for you to comment on. Coming back from ancient Greece to more modern days, so how can we make the journey for lithium easier in terms of the structures and the architectures of the anodes and the cathodes? In other words, what would be an idealized architecture to impose longevity and stability? So as we've seen the perpetual tortuous journeys that they go through, don't need to go through this again. This is just attempting to show the importance of balancing ionic and electronic conductive pathways and how these need to be balanced and uniform so that we can achieve a Coulombic efficiency and an effective use of the battery. And so for a long time, since the advent of battery electrodes, understanding what constitutes the perfect microstructure is quite challenging. So here we can see these are typical graphite newer cathode chemistries. What is the idealized active material in terms of particle size, chemistry, polydispersity, dimension, morphology? Similarly, for the conductive materials that we need to add, do these need to be a combination of particulate, high aspect ratio, sheet-like structures? There's a lot of systematic research has been done on different types of material, because we know in not only battery materials that any functional microstructures, how they're made and the design has a big influence on the functionality. And so by designing optimized electrode morphologies, this is actually key to battery performance. But to date, optimization of battery electrodes and materials has been done by way of very empirical optimization, by sort of lengthy systematic laboratory experiments based on very big matrices that can be very time consuming and actually quite expensive. And so in more recent times, virtual material and coating design using advanced fabrication techniques have been critical and will continue to be so if we're really going to make or want step changes in lithium ion performances. Some of the advanced methods will look at different types of layering. What is the optimal core network infrastructure? Other types of specific design to look at how spheres are packed for cathodes, or how power cell electrodes can have their microstructures optimized. So some recently interesting projects in Faraday Institution repertoire, Nextrode, for example, looking at graded electrodes, whereby you can deliberately put down different materials in a gradient of composition and porosity to try to design the perfect functional microstructure, whereby, for example, lower resistance layers nearer the current collector, different types of porosity gradients nearer the separator, particle size to have a more efficient packing density without compromising the penetration of electrolyte. And so a better design, just rather than relying on this monolithic combining different materials and dispersing them well and hoping for the best. So this will give us much more control over what an idealized microstructure would look like. So as well as how we can make things in the best way, how we characterize them in operation has also been very illuminating in our understanding of degradation modes. So now for the last part of this talk, I'd like to talk about how useful operando characterization has been. So why operando, why in situ? So there are a lot of multi-phase complex reactions that take place inside batteries, both chemically and structurally. And understanding these by relying on ex situ measurements, or waiting for batteries to stop operating, then taking them apart and examining their components, you lose a lot of information because they're very reactive and very rapid reaction mechanisms that occur during sealed battery operation, whether it's structure evolution, redox mechanisms, interfaces and solid electrolyte phenomena, parasitic side reactions, diffusion phenomena and degradation. And so just relying on post-mortem analysis, you can really limit the amount of data and information you can get, because ultimately, because lithium compounds are very reactive to moisture and oxygen, when you open them up, even in a glove box, you can lose a little bit of information. So real-time, multi-scale analysis, operando, and in situ has been absolutely vital. So then looking at the sort of repertoire of techniques that you can use to look at environment, structure, interfaces, etc., whilst under electrochemical operation, broadly speaking, we can categorize the type of operando technique by the sort of source of excitation energy used to generate the analysis and detection. So whether it's X-ray, electron-based, optical mode, scanning probe type microscopy, nuclear or neutron, a lot of operando techniques have been developed over the last decade or so to better understand a whole host of physical and chemical reactions over multiple length scales, from the micro to the meso to the macro, with quite impressive temporal resolution. You're going to start to see a lot of acronyms, which I won't be defining all of, but starting with the X-ray sources. So techniques such as XRD, XPS, which are X-ray diffraction, X-ray photoelectron spectroscopy, etc., have given us a lot of very valuable information about structural phase changes, surface, and indeed chemical information. Electron-based techniques are a lot of imaging or high-resolution imaging techniques such as SEM, TEM, which can give us good feature information as well as crystallinity properties and surface type information of topography, etc. Optical-based techniques can identify molecular bonding and are typically Raman or FTIR type techniques that use respectively laser or infrared type excitation. The scanning techniques can look at things like probing diffusion layers or localized electrochemistry mapping. Techniques typically such as AFM or atomic force microscopy, scanning electron chemistry microscopy, and SKP. We can also look at structural changes and metastable phases with things like multinuclear NMR techniques, which have been very useful at looking at metastable phases. Cambridge have made very, very good progress in this area. And then finally, the neutron-based techniques can quantify structural changes and look at real-time lithium distribution. So all of these have made enormous leaps and bounds in our understanding of degradation mode since their development. But they can be quite challenging techniques to do well because they all involve bespoke cell types to allow for the simultaneous analysis and electrochemical activation of the contents. So this is just a snapshot of various different types of cell to use for various techniques. So X-ray microscopy would use a cell like this AMPET cell. TEM, obviously you need to be able to transmit an electron beam through the entire cell, so you'll need an appropriate window. And most of these cells, whether they're for X-ray, TEM, SEM, other generalized coin cells, pouch cells, they all need specialized windows to allow either X-rays, electron beams, RF energy through, and to be able to be connected up to potentiostats to be able to analyze and detect and analyze the desired changes that occur within. And also the design of the cell needs to not interfere with the electrochemistry so that what you're seeing is practically relevant. And other funky things you can do with characterization is to look at restitching together the scans to be able to see through the battery devices to internal features. You can see here the prismatic squash jelly roll or mandrels inside cylindrical cells. So it's quite nice to be able to do some nice sort of graphics like that. Also, you can look at real-time degradation events. So the video I'm about to show is actually showing a growing copper dendrite growing between two deposited lines of copper. It's not a lithium dendrite, but it's illustrating what a growing dendrite could do to end in a short circuit. You may be able to hear some music, but it shouldn't interfere with the video. So this is showing corroding copper growing through water. And you can see the fractal branching. And that would have constituted a short circuit when it touches the other metallic surface. So a lot of operando techniques can be really useful for just visualizing real-time and analyzing real-time chemical and structural changes. So to conclude, that we've seen that during the charging and discharging of lithium-ion batteries, capacity fade occurs through a whole host of different mechanisms on both the anode and the cathode, and that there are multiple degradation modes, and they don't all occur in isolation. They can occur simultaneously, which can sometimes make them quite challenging to analyse. But by reducing side reactions, by stabilising interfaces and avoiding losing lithium, this will benefit the lifespan of battery components and add efficiency to operation. But I think it's fair to say the continued journey into developing better operando understandings of degradation will continue to facilitate advances in how we manufacture the components and which materials and additives we use. I would like to acknowledge before finishing the SCItalks team for this, and apologies for any technical issues my side. Big thank you to David Bott for linking me with SCItalks. I would like to acknowledge Professor Lewis Piper for his input and guidance to this slide set, and big thanks to WMG as a whole and the Faraday Institution. But more importantly, thank you all for listening. If you are interested in looking at the Energy Innovation Centre details at WMG in the University of Warwick, these are some links, and also to the battery forensic website, where we are developing a lot of in-operando characterizations. And with that, I will close and invite any questions or indeed any answers.
Right, so thank you for an excellent talk, Melanie. Before we get to the Q&A, I just have to do a word from our sponsors, as it were. This is one of a series of talks which used to be public evening lectures until we couldn't have people in Belgrave House, and they became SCItalks at that point. In just over a month's time, we have Richard Jones, ex-Sheffield, now at Manchester, talking about the role of the chemistry industry in the UK's economy. About a few weeks later, we have Ruth McKernan talking about a quest for effective dementia treatments. And a month after that, we have Carol Mundell talking about black holes, gravitational waves, and other astrophysical things, which just encapsulates the breadth of the whole sort of activity here at the the Society of Chemical Industry. Also, there's a lot of work by the individual committees, in particular the Fine Chemicals Group and the Young Chemist Panel have been holding weekly webinars over the last couple of months on a whole range of things in process chemistry, medicinal chemistry, and such. They are truly wonderful. I've learned more chemistry this webinar series than I have done in a long while. And of course, all these are accessed by being a member of the SCI. You can hear them outside, of course, but we prefer you to join, and you'll know about them in advance. And also, you get a truly excellent magazine, C&I, and that's worth having at £75 alone. Okay, so I think now it's time to go to the questions, if that's okay with you, Melanie, and hopefully Bryony is ready with the questions. So let's go.
Yep, so our first question is from Marche, which is about lithium plating and dendrite formation. So the question is, lithium-ion technology is widely known and has been studied for years now, but we don't hear much news about lithium metal batteries. So what is the current stage of lithium metal anode development, especially stopping dendrite formation and any other countermeasures against lithium plating in subambient temperatures?
Okay, well, there's been a lot of research being conducted on lithium metal anodes, in particular within lithium sulfur systems, but more broadly that, you know, the lithium metal anode is still seen as the holy grail. So when it comes to approaches such as surface engineering or coating to stabilize the concentration of lithium ions, to try and regulate better this sort of stripping, plating cycle, but also just trying to generate even a more uniform electrical field near the surface. But ultimately, rather than complete suppression of dendrites, it is more the regulating them that is critically important. And, you know, as well as the sort of physical engineering of surfaces, more sort of in situ approaches such as additives to electrolytes that can control morphology to create more uniform plating rather than sort of high aspect ratio dendrite growth. A lot of areas in that domain are making leaps and bounds. Certain, to mention companies, Oxis Energy, who've been developing lithium sulfur batteries, have done a lot of good, very good work on passivating the surface of the lithium anode to try and better regulate that detrimental growth of lithium. So there's a lot of effort and enough lithium in the world to hopefully succeed at that.
Melanie, you said there are additives you put in the electrolyte that inhibit the growth of dendrites. What sort of things are they? Are they the same strong compounds, or are there a large number of chemicals that do that sort of job?
Well, one of the promising candidates, potassium salts. Certain salts have been, with different anions, been shown to be able to control, sometimes in some cases with certain compounds, they can actually mitigate plating.
Okay.
But this is still at research stage, and to my knowledge, I don't know of any commercial systems, commercial electrolytes that have these additives in, but I dare say, you know, university academia research is one thing, but behind closed doors in industry, you don't get to hear about a lot of these.
Interesting to think how they work, because it's a bit like, you know, how you control crystal habits in other environments and things like that. It's a fascinating field of physical chemistry, really, isn't it? Okay, well done. Thank you. Brian, another question?
Yeah, so this question is from Marat, who says, does CEI increase the resistance like SEI? Thank you.
Yes, well, CEI and the SEI have similar compositions in some respects. Obviously, they're at polar ends of the voltage window. And depending on the anode material in question, SEI can sometimes be a bit thicker and more continuous. But what the CEI will do, of course, is to add interfacial resistance at the cathode particle surface, and this will affect the kinetics of charge transfer. So yeah, it does. It can. And if the composition, whether, you know, a combination of organic and inorganic phases, if they impede ion transfer, then yeah, that will significantly affect the resistance internally.
This one's from Sushil, who says, could you explain how voids develop on the cathode microstructure, and if nickel is the material that drops out creating voids, then how are high nickel cathodes compensated to avoid voids?
avoid voids. Yeah, that's a good policy. Yeah, no, this is particularly fascinating. I'm a keen microscopist, and the number of sections of electrodes I've dug out to look at, and yeah, it's really interesting. So with the high nickel materials, as we covered in the slides earlier, you know, they're secondary particles composed of a lot of sort of submicron sort of nanograins. And when you get them expanding and contracting in different directions, you get disconnects between the aggregate. And if you've got simultaneous electrolyte gassing going on, some grains can become disconnected and dislodged, and with expansions going on, you can get sort of subparticle movement. It's not a clear-cut mechanism, but in the high nickel materials, for example, of, you know, a lot of intense interest, certainly the ones that have 8 times the stoichiometrical content of nickel compared with the other transition metals. So it's not just like it's the nickel being dislodged. The nickel is more importantly lost through sort of surface dissolution reactions. So the actual void formation is a bit of a complex interaction of like the expansion properties, some movement and disconnections. But as I say, that mechanism isn't 100% clarified yet, but it will add to, again, more impedance and challenges to retaining capacity, because if you're losing, if you're isolating materials, then, you know, you're not accessing all of the active particle to achieve reversible Coulombic transfer.
Yeah, so the next question is from Yun, who says, very nice talk. What is the impact of binder on the formation of SCI and stability of the electrode?
The polymer binder. There's a lovely paper called, was it Small is Beautiful, or Small Things Make a Difference? So in both anode and cathode coatings, the polymer binder is one of the least percentages by mass occupied in the whole coating. So typically anywhere between a couple of percent up to maybe 5. Academics tend to put a lot more polymer into their electrodes than industry. So not only does it have the critical function of keeping the coating onto the current collector, but it has to keep all of the constituents of the coating cohesively attached. So this includes all of the conductive carbon networks to the active material. Good binders tend to covalently interact with active surfaces to just maintain that mass, so that you get optimized ionic and electronic transport, or connectivity rather. Situation becomes critical with binder chemistries when it comes to materials that undergo more severe volume expansion, in that they have to retain physical connectivity with the particles. And so I think that is the most important thing. And of course, you know, the chemistries themselves will have different functional groups, will have different tensile and mechanical properties. So having that balance of chemical conductivity or connectivity with flexibility is one thing. Having chemical resistance to dissolution in the electrolyte solvents is really important as well. This is why one of the workhorse polymer binders that's been used since the early 90s, PVDF, as I'm sure the acronym known by battery scientists, it has really good chemical resistance, but it has very poor functional interaction. And so it's all a bit of a balance, but ultimately chemical stability, physical flexibility, temperature resistance to a degree, but favourable interactions with electrolyte solvents. But coming back to the section of the question about the SCI, because when you consider the surface area of all of the particulate elements of an electrode. The binder, it doesn't cover all of the surfaces. So in terms of how it really interferes with the SCI mechanism, that's quite a tough one to quantify. But you know, the formation of SCI and CEI are actually quite important. And so if the binder totally encapsulated every particle, batteries wouldn't work as quickly as they do. So it's a bit of a compromise between surface anchoring, but allowing sufficient SCI to get that passivity, if that makes sense.
Yeah. Melanie, I mean, you talk about it doesn't do this, and you know, you talked in the talk about the particle size and the particle size distribution, and it's each particle is made out of subparticles and such. I mean, it all sounds like a bit of a soup in some senses. I mean, if you could layer up a material by complete atomic design, do you think we know enough to design a perfect battery cell and get rid of all these problems, or are we always going to be compromising on the additives?
Wow, that's a very good question. And I'm sure, as you know enough about batteries by now. There's been a lot of iterative or empirical approaches to, you know, what works best in formulations, which types of additives, what is the perfect microstructure. And in all honesty, I still don't think we know. And despite,
but that keeps us all in research, though, doesn't it? Let's be fair.
Yeah, absolutely. And you know, as battery manufacturing, lithium-ion battery manufacturing has progressed since the 90s. You know, we have borrowed from a lot of other industries, whether it comes to the processing equipment, the sort of design of the composite films. And I think we're continuing to learn, but I have to say, and again, this is my subjective opinion, but I think there's been too much reliance on just the electrochemical cycling and not enough big data approaches to really integrate how each of the properties of the materials functions in a hierarchical manner under electrochemical operation. I really do think we need that big data approach to.
Yeah. No, yeah. It's called electrochemistry because electrons go one way and chemistry happens the other. But chemistry happens, and part of the problem with all these things that go wrong are when chemistry gets to be irreversible rather than reversible.
Exactly. Absolutely. Yeah. And of course, you know, and a lot of that will always be down to how efficient the structure is. So, you know, you've got the electrochemistry bit, you've got the chemistry bit, you've got the structural bit, you've got the electrical, the thermal, the mechanical. They all orchestrate into this domain that all needs to work in a balanced, homogeneous way, and they don't.
Yeah. And then I think it's interesting talking to our friends and colleagues that you know, the requirements of a battery that goes into a mobile phone is that it has to be more or less between 15 and 20 degrees and work. If you put it in a car, it has to work at -10 and +30 and all those sorts of things. And all that chemistry, I mean, if you think of most chemical reactions and the change in rates over those sorts of temperatures, it's just amazing that they work at all.
Absolutely. No, I was going to say, and you know, that's where parallel advances in management systems and the sort of the hardware side of things really does come into its own in maintaining that optimized operational environment for the battery, because you know, the chemistry is I think obviously the most important, but I'm biased, but it has to happen in a zone where it's thermodynamically and kinetically happy. And so that will really rely on temperature and the ability to control the conditions around how it works.
Excellent.
Thank you. Yeah, so maybe slightly less technical question, but you mentioned at the beginning of the talk that further innovations are required for battery recycling. But what kind of time frame is there for this to be fully integrated into the supply chain, and what innovations are required?
Yeah, very good question. Whilst currently the UK doesn't have a large volume lithium-ion battery recycling facility, there have been a lot of pilot schemes. EcoSurety, Belmont, I think, to name but a few. But in terms of timeframes and to optimize, so hydrometallurgical and pyrometallurgical processes are the basis of being able to separate out and sort of reprocess a lot of components of lithium-ion batteries. But if all of the batteries that are coming off production lines now, if we are to adequately and efficiently be able to start handling production volumes, we will need high volume recycling facilities by the mid-2020s, I would say, to ensure a sustainable automotive solution. But also, I mean, it's not all about recycling as well. So a parallel option there, obviously, automotive batteries can be repurposed. So ultimately, of course, they'll still need to be recycled. So I think, yeah, the mid-2020s, and when you consider how many gigawatt hours of global batteries are going to be predicted over the next few years, yeah, I mean, I know Belgium has a recycling facility, but yeah, it does need more investment. But the UK, you know, fully aware of that, and with the desire to generate our battery supply chains and to use sustainable designs and, you know, threshold percentages of recycled materials in battery manufacturing, yeah, I think we are.
And you know, if those who've been paying attention in the talk will realise the complexity of the battery means that all those different pieces have to come out to realise as full a value as possible. So it's a non-trivial task, I think, is the understatement of the year.
Yeah, absolutely. But the potential benefits are enormous if we get this right.
Yeah, good one.
Thank you. So maybe a couple more technical ones. So Mache says, is monocrystalline NMC more durable than polycrystalline in the case of cathode degradation?
That's a nice question. Well, the beauty of monocrystalline materials is that in terms of the diffusion and movement of lithium ion throughout them will be more uniform, and certainly any crystalline expansion and dynamics in the lattice crystal structure will be more similar. And so, and what would be avoided with a single crystal compared with the polycrystalline is, when you've got a collection of grains in a big particle, a lot of them expanding in different directions, leading to microcracking, leading to structural breakdown. One could argue that that will be a lot better in terms of a single crystal material, which will then avoid resistance buildup, will allow more consistent diffusion rates, which would, in theory, improve the rate capability. And also, in terms of the manufacturing and the synthesis of these materials, there's been a lot of progress in being able to make consistent dimension particles, which is always a good thing from a rate perspective. If you imagine a big box where you've got like tennis balls, ping pong balls, ball bearings, and that polydispersity versus rate capability and energy density is always going to be a bit of a trade-off. But with the means of, and actually quite economically viably making similar monodisperse single crystal materials, does hold a lot of promise for being very effective cathode materials.
Okay, I think we should probably call it a wrap there. Melanie, thank you for a truly wonderful talk and some great answers to questions, and some really good questions from the audience as well. As usual, this will be up on the SCI YouTube website within a few weeks, when we've edited out all the bloopers I make and that sort of stuff. And so I'd like to thank you one more time for taking part, and particularly to our speaker, Melanie Loveridge. If this was the real world, Melanie, you'd hear lots of applause at this point. So thank you very much indeed.
Thank you to SCI.